Well, happy Tuesday, everyone. I hope you had a good holiday weekend. Celebrated MLK Day. So it took me a little while, but I did post the video for last time. As you may have seen if you already watched it, I just re-recorded it at home because my camera was pointing weird for half of it, so you couldn't only see part of the screen. So it's a little bit faster than I normally do, but anyway, hopefully, along with the PDF, it's enough to go back over anything. If you ever have any questions, feel free to ask in class, send me an email, whatever your preference. Today, we're going to get a little bit more chemical than we've been so far last week. So apologize for some of you if that is not so much to your liking, but in any event, just like in a language immersion class, I'm going to use the language of chemistry. And if some of the terms I use are things that you heard, but you don't quite remember, or you don't know, or whatever, ask or consult the background reading or consult the chemistry review pack, so that we're up to date, because I do use terms related to chemical equilibria and solubility and Lewis acids and Lewis bases and these kinds of things. And so if those are terms that maybe you need to refresh yourself on, please do it sooner than later. So we've got kind of four main topics. They'll be divided up into some topics. But we're going to talk about natural waters and TDS in them. We introduced TDS last time, total dissolved solids. We'll talk a little bit more about the composition of that. Then we'll make some other generalizations about how things that dissolve in water behave, and then the limits of dissolution, as well as the mechanisms of dissolution, which are not always the same. And then we'll finish off today talking about complexes, chelates, behavior of ions in water in the presence of complex agents, which are usually Lewis bases. It'll become really important to also be familiar with where things sit on the periodic chart. I try to point to it a lot during the class, but certain elements we will see require these things to be able to be dissolved in a lot of natural water. Okay, so I think we've all seen waters that we looked at in nature that look like this and that look like that. Particulate matter is something you can see with your eye. Solutes, you usually can't. Some solutes, if they're in high enough concentration, you can, especially organic solutes, which tend to have a slight yellowish tone, and many of them, not all of them. And so we want to do better than this to understand why it is that things get the compositions that they get and how. And even though we're going to talk about contaminated environments a lot, we have to think about natural processes as well. How does water get the composition that it has? And not just what's dissolved in it, but also some master variables like what's the pH of that water? And how did it acquire that pH? Is it full of oxygen or less than saturation with oxygen at whatever temperature it exists with in equilibrium with the atmosphere? And various other parameters that affect how other stuff in water behaves. Okay? So we got to think about a lot of natural processes because these affect how contaminants enter water, how they behave when they're there, etc. Now when we go to remediate, which means to clean up, we have to think about these sources added to the sources for the contaminants. And when we think about sources and what we call reactive sinks, which are things that naturally remove chemicals from environments, these are fluxes. We talked about fluxes last time. So we're looking in a reservoir. It has a concentration profile of something or multiple things that we don't like. We've got to figure out where those things come from, where are they going, how are they affected by natural processes superimposed upon by contamination. So it's a kind of a whole package deal. So when we talk about natural controls, there are a lot of different things that happen. And I actually think this slide is a repeat of the last slide where I expanded the word, so I'm not going to do it anymore. I think I accidentally duplicated it. So this is some of the things, some of the processes that set compositions of waters. And most of these are natural, although you can see in some cases, obviously things you in your mind's eye, you can imagine where humans impact them. But we have all these chemical reactions that are put in the category of inorganic, meaning not really involving organic chemicals. These are acid-base reactions, dissolution of minerals, the dissolution of salts and precipitation thereof, solubility of gases, reactions on particle surfaces. We're going to spend a lot of time talking about this, but there are chemical interactions that happen with things, chemical moieties that exist on the surfaces of particles that to a solute looks like it's in solution even though it's not. And the kinds of chemistry that happens is very similar to the kinds of chemistry that happens in solution. Then we got some biological processes, photosynthesis and respiration being key in environments that are oxygenated. There's other analogous processes that happen in anaerobic environments, which we'll talk about. OM is my abbreviation for organic matter. So complexation and chelation reactions that happen between organic matter in solution and other things that have been dissolved primarily by these inorganic mechanisms. Redox, maybe you remember this term from a chemistry class where you learned about what makes batteries work. It's the exchange of electrons, oxidation reduction reactions, very important in the environment, primarily driven by the master variable of the presence or absence of oxygen. Then we have all these physical conditions. If we've got water that's moving, how is it moving? How fast is it moving? Is it moving intergranularly? Is it moving in a different form? What are the particles? How many of them? What size and shape are they? What are their surface areas? How chemically reactive are their particle surfaces? What's the size of a reservoir that we're interested in the composition? Is it big? Is it small? And obviously, what's the temperature and the pressure? All these things affect compositions. So I like to think about water in a watershed as moving along a flow path and acquiring composition in an integrated sense. Right here, we're in Manoa Valley. The water that comes out Manoa stream or as runoff, maybe on the street, starts as rain. Some of it percolates into the ground. Some of that interacts with solutes in the ground, comes back out in the form of springs and feeds surface water. Some of it just runs straight off. But in any event, there are various processes that go along that change the composition of the water. And these include inputs from local solids, from gases in the atmosphere, as well as the local biosphere, right? So if you look at two exact carbon copy watersheds, one with plants in the watershed and one without, you're going to see very, very different compositions in the water, primarily because of the presence or absence of organic solutes within the water, as well as organic particulates, which affect a lot of attributes of the water. So we have to think about things along a flow path and how things might change, as well as the residence times in that system. And this is just an example of some of the physical parameters that play a role in a watershed. This is an urbanized watershed that might affect composition. Things like these things that vary as a function of season, things that vary as a function of the geomorphology of the environment. You can imagine how these things work together. If we have high seasonality in our rainfall, for instance, we may have periods of high flow or low flow in our surface water. We may partition the amount of water that flows on the surface versus the subsurface differently during those times. And those waters may encounter different substrates to interact with. There's the sort of velocity of the water, which affects many things. Not only does it affect how many particles it can hold and mixing in the water, such as aeration. So in deep water channels where they're particle rich, sometimes light doesn't penetrate all the way to the bottom, and we don't have full mixing of oxygenated water from the surface down to the bottom. If we have a very turbulent pattern, then that might happen. When this water emits out of that landscape, and here in Hawaii, it's mostly straight into the ocean, we have questions about how does it mix with salt water? Does it mix in a laminar way? Does it mix in a turbulent way? Over what geophysical domain does it interact over? Because there's going to be some big compositional changes that take place at that interface, and we'll talk about those later. Then there's stuff like what have humans done to the landscape, and you can imagine what all those things are. There are big differences in compositional attributes of the solid materials in an urbanized landscape, as well as the particle concentrations and types. Typically, much more dense particles can come off of an urbanized landscape than a natural landscape. And then we have all these things over here, which are kind of more in the category of what is the land made of, as well as how is the land being used. You know, what are the particulate materials, how did the soil form, where did it form from? We'll have a whole week where we talk about that. What is the rock made of, and what is it texturally, how does this influence that? What are the biogeochemical processes in the watershed? All these things are things that we're going to be talking about during the semester. For now, I just want you to realize that in this idea of integrated compositions, if we collect some of this water and some of this water, our hope is to try and explain the difference in compositions by all these kinds of processes. Sometimes some processes are more important than others, but that's kind of our goal. All right, so this is another kind of flow chart that just shows you some of the things that can happen as physical conditions in an urbanized landscape, such as the one that we live in here, that might affect composition as a course of change. And so it's divided up into a couple of different things. One is human activities that don't involve land use, and the other one is land use. These are obviously both human type things. But you can see the sorts of things that happen here, such as how have these sorts of things like traffic and the amount of green area and the amount of water consumption by residents and businesses changed over time. What happens with the wastewater? Does wastewater always make it from its point of origin to the sewage treatment plant, or does it leak sometimes? How does it leak? Where does it leak? Contaminants that run off the land surface into the water. Heat, which is something that is concentrated in urban areas. And on this side, we have stuff like what's happened to the soil? Have we compacted it? Have we covered it over with asphalt or concrete, which limits percolation? Have we changed the way water flows off the landscape by channelizing it and making it flow more quickly, and therefore picking up more sediments and less chance of percolating back into the ground? And what are the impacts on things like runoff, the local cycle of evaporation and precipitation, and what, if anything, are the changes of the impacts of climate variations that cause flooding or drought? So there's a lot of parameters that go into these things, but as you can imagine, any one of them, if big enough, could have a big impact on what is flowing off the land surface in the form of water. So if we start at that start and we say rain, okay, let's look at the rain here in Manoa or somewhere else. How does it get its composition? It gets a composition in two ways. Mostly raindrops nucleate on little particles that we call aerosols. So those particles can take a bunch of different forms. There's also gases in the atmosphere, right? So if we have, obviously we have oxygen, we have carbon dioxide, we have some acid oxides, sulfuric acid, nitric acid precursors that can contribute to the acidity of rain in some places. But the primary compositions are from particles. Okay? And these are the kinds of particles that we find. So that's something called the marine rain component, which is primarily sea salt. Desiccated little particles of seawater that get up into the atmosphere. So the rain that comes back down in marine areas or in island environments or even coastal environments on the continents pretty much looks like dilute seawater, very dilute seawater. That's what our rain looks like. But you also have terrestrial particulate inputs, dust, soil particles, volcanic emissions in our case, pollen, other plant materials, smoke. And you can imagine how some of these things, in this case, I've listed them all in natural categories. All these things get into the atmosphere. But humans can enhance some of these things, particularly dramatically. And then added to that are these non-natural particle sources. So I split them up into industrial particles and agricultural particles. And you can see these things, you know, certain kinds of soot and automobile emissions and things that come out of bakeries. Think about the plume of smoke when they're flame broiling your Whopper. Agricultural particles, which can include enhanced rates of emission of dust and soil. Think about tilling fields and big plumes of stuff going into the atmosphere. Fertilizers, pesticides, the list goes on and on. So we can kind of sort out these components in rain by saying, which things do we think come from this? Account for as much compositional attribute from that as possible. We'll see how we do that. And then look at how much stuff we can explain by this. Anything we can't explain by these two things, we start to look for these kinds of processes. And once that water hits the landscape, it starts interacting with other things on the land surface. These chemical legacy that is in the rain starts to become overprinted and more difficult to see. But there are occasions where we can find contaminants in watershed water that initiated from the rain cycle. And so that's why we start there to at least understand what the water came with before it hit the land surface. So then there's some other considerations, which is, all right, we put stuff in water, how does it behave when it's in the ground? The terms that we use in geochemistry are conservative and non-conservative ions, okay? There's an equivalent concept in biochemistry, and all conservative means is that a conservative material is for some set of master variables. In the case of natural waters, we think about the pH, the temperature, and the pressure primarily, if we're in equilibrium with the atmosphere and oxygenated. If we're isolated from the atmosphere and therefore lower oxygen, then we also think about this other parameter which measures redox state. We'll define it later. It's called PE. It's analogous to pH. But these are our three master variables. And a conservative ion or conservative solute, it could be something like methane gas or something like that, the ratio of one conservative chemical to another doesn't change, even if the water changes in these parameters. So they behave conservatively in the sense that they're usually very soluble, and they are not, their solubility is not sensitive to how acid or base the water is, how warm or cold it is, and what the pressure is. And pressure becomes important in places like the deep sea or deep groundwater. Non-conservative ions vary as a function of these things. So whenever we're trying to categorize an environment, we always look for some conservative chemicals in there because they are less likely to have been affected by some of these major variations. Figure out how much is there and where they come from, and then look at other elements or ions or solutes relative to them that are non-conservative. And you can be a little non-conservative, or you can be a lot non-conservative, right? There's no shades of gray with conservative, but once you stop being conservative, there's a gradient to the maximum non-conservativeness. And that will help us understand what is controlling compositional variations. There's lots of other things besides these variables, but we try to look at these things first because there's something that's pretty easy to measure and determine. Okay, so here's an example of a watershed where we've got conservative and non-conservative processes. And we're going to talk about this kind of process in gory detail where we have water coming off the land surface in a river, coming into an estuary, and then exiting out the ocean. There's a whole bunch of really interesting chemistry that happens there. We're also going to talk about these stick figures in more detail. For now, you can just think about these as organic compounds that are soluble in water, in these cases, and organic compounds that are sparingly soluble in water in that case. And again, those will become clearer later. But the chemically conservative chemicals are mostly non-reactive in a system like this, where we've got water coming off the landscape and all those things that I showed you a couple slides ago that happen, interaction with the land surface and runoff and land use, and et cetera, et cetera. And so therefore the concentrations in the outflow are relatively stable with time. They could have effects from pressure and temperature that are relatively minor, but because they're conservative, we don't expect very much variation from them. We also, because they're conservative, typically expect a long residence time. Long residence time in a lot of environments equals high solubility. Something that goes in the water and it stays there tends to give it a high residence time. Right? There's short residence time, something that gets in the water and it doesn't like to stay there. Maybe it's insoluble or maybe it sticks onto some part. So some of the processes that make things non-conservative include biological reactivity. Maybe it's an organic chemical that gets composed by respiring organisms, or maybe it's something that gets acted upon in another way by organisms, like a fertilizer that becomes nitrate ions, for instance, that become absorbed by photosynthesizing organisms. Maybe it's chemically reactive. There are changes in chemical composition as we go through this flow path here that could affect how sparingly soluble things, how soluble they are or not. These kinds of elements tend to be variable over time and have short residence times. And you can see some examples here. These are just examples for this particular environment. We'll go into the kind of details of these things later. I'll just tell you some of the abbreviations because I use them a lot. OM is organic matter, so DOM is dissolved organic matter. Sometimes, and including in this particular paper, people equate DOM and DOC. DOC just stands for dissolved organic carbon. I tend to use DOC more often than DOM, but you'll see me sometimes slip back and forth. We also have something called POC, which is particulate organic carbon, and those two phases become really important, especially as we change the flow field and we start to partition whether things are dissolved or flowing as particles or sedimenting out. And as I say, we'll talk about these terms when we get to organic chemistry more. TDM stands for total dissolved nitrogen, which is another water quality parameter and tells us something about the relative balance between photosynthesis and respiration on the land surface and in the watershed, which equates to another term which isn't on here called BOD, which stands for biological oxygen demand, which is another master water quality parameter, which tells us how much digestible organic carbon that respiring organisms might like to compose is present, and therefore what is the potential for our water to go to low oxygen concentration in the presence of that BOD and organic, respiring organisms. So we kind of get down to the brass tacks of the simplest types of conservative ions in inorganic solutes in things like the oceans or a river water. This is the list here, okay? All of these are major ions in seawater. In fact, these are the top ones. The lowest on the list is potassium, followed by calcium. But seawater is primarily a solution of sodium, chloride, magnesium sulfate. You'll see nitrate is on there, but I put it in red. So in many books, they consider nitrate, in the absence of organisms, a conservative ion. In the presence of organisms, it isn't, okay? So think to the example I gave you last time of an oligotrophic lake and a eutrophic lake. An oligotrophic lake with very few biological processes, we would see nitrate behaving conservatively. But as soon as we put a little bit of organisms in there, it stops behaving conservatively. So I tend to not think of it that way, although chemically it is conservative. So what that means is that if we can look, we can go across all the oceans, or we can look at other solutions that are primarily of a similar composition, we'll find the same exact sodium chloride ratio. Concentrations might be different, right? We talked about salinity last time. Salinity can be high or low, so the absolute concentration of the salts goes up and down, but the ratios don't. The sodium to sulfate ratio, the magnesium to chloride ratio, these are constant because those are conservative elements. There's very few things that can alter that. Now let's look at the non-conservative things. This is a simple list of some of the simple chemicals. And you can see that most of them are anions, first off, negatively charged compound ion. These two, bicarbonate, I use this term a lot, so please remember it, and carbonate are the end products of the dissolution of carbon dioxide into water. You drink a lot of soda, you drink a lot of these things. Although not as much as you might hope, because they put phosphoric acid into a lot of sodas to bring the pH lower. But in any event, these things are present, and how much of them is present is very dependent on the pH of the water. Boric acid, this is the anion, BOH4 is the acid anion of BOH3. Again, this is one of the 10 major ions in seawater. Very soluble, but the relative amount depends heavily on the pH because the transformation between BOH3 and BOH4 minus is very pH dependent. Then hydrogen sulfide and ammonium, which is the cation form of ammonia. These things are also very pH dependent. The relative amounts of these things is going to vary a lot from place to place, just as things change with temperature and pH, and to a lesser extent, some of the other parameters, such as pressure. Then we have phosphoric acid and all of its conjugate bases. This is a triprotic acid, so H3PO4 can dissociate to H2PO4 minus, and that can further dissociate to HPO4 minus, and finally the phosphate anions, PO4 minus. The relative proportions of these things is heavily dependent on pH. Like nitrate, this is also something that's very easy to consume out of environments in the presence of organisms. Again, we'll talk about that later. And then this kind of large box, which is most organic anions. So as we will see, many organic chemicals, except for hydrocarbons, which don't have acidic hydrogen ions on them, most organic molecules are acidic. We stick them in water, they lose a hydrogen. Think about acetic acid or something like that. And again, we'll talk about the details of this in a couple of weeks. But the important thing to recognize is that when we stick biologically produced organic matter other than hydrocarbons into an environment, it loses hydrogen ions, contributes to the acidity of the water, and makes an anion. And the presence of these things becomes very important, as we'll see later today, the solubility of many chemicals in the periodic chart, particularly pretty much the entire middle of the chart. Most of these elements are not very soluble in water unless they have something to solubilize them, which tend to be organic acids. So these are just some of the examples. We also have other low solubility non-conservative ions like the dissolution products of silica that comes out of silicate rock. So this, you have a question?
Is that ammonium on the top?
Yeah, that's ammonium. Yep.
Okay. Thank you.
Sorry, before should be a subscript. Sorry, yes, thank you. Okay, so next process that we want to talk about is dissolution. You might think, oh, dissolution, right? Put powder in my coffee, it dissolves, salt in my soup, whatever. It isn't quite so simple. It turns out that there are two fundamental processes of dissolution. One of them we call congruent, which means that as a particle dissolves into water, it dissolves completely to the extent that it can. Like we can get to a saturated solution. If you like drinking sweet tea, you put more sugar in there than the tea can hold. You'll still have particles down below. But the point of congruent dissolution is that every bit of stuff that dissolves, fully dissolves, and any solid left behind is the original solid. That is distinguished from something called incongruent dissolution. In incongruent dissolution, parts of a solid will dissolve, leaving a new solid behind. You can think about this as sort of like the process of chemical leaching, like we're sucking some stuff off of a particle and leaving other stuff behind. This is the primary process through which soil particles are formed. They're really fundamentally different in a lot of different ways. As you can imagine, let's say we have solids in the subsurface and water's flowing through them and they're dissolving congruently. We're going to increase the porosity of the subsurface, the pupas that are present because we're dissolving the solids. Whereas in incongruent dissolution, water is flowing through and we're changing the solids, but we're not removing the solids, we're just changing what they are. And therefore it doesn't change the porosity as much. In some cases, these new solids can be less dense than these, and we can start to cement out our aquifers or whatever. So we want to understand these two differences and their impacts when we think about the solubility of materials. So this is a diagram. I realize it's a little bit complicated, but it shows you scenarios for congruent dissolution across the top and incongruent dissolution across the bottom. So let's just look at the simplest case here. This is some chemical A, it's in the solid. This sort of dashed line is the solid. And we're going from some initial time, T0, where the solid extends out to the point of X0. And then we give it some time and it dissolves. And this boundary has migrated back to X. Okay. And congruent dissolution, a chemical, whatever it is, let's say it's sodium ions, is constant up to the boundary. And then right when we get to the boundary where it's now missing, that concentration changes. So it's gone into the water and obviously mixed in with the rest, and so the concentration goes down. Now, if we come to one of these cases that are incongruent, and there's a couple of different ones, this is a case where this boundary doesn't change. It's got a different Hasher pattern, and you can see sort of one area, a boundary layer, another area of change composition, and then a natural composition. And then we can look at some chemicals in there, like the profile, concentration profile of silicon, aluminum, and sodium. We see that once we get to this gradient area, silicon goes down, aluminum goes up, and sodium goes down. Now, I'll give you an example of a chemical reaction that's super important in soil forming and in weathering. This is the reaction of potassium feldspar with hydrogen ions in water to make kaolinite clay, dissolve sodium ions, and dissolve silicon. This reaction makes one solid turn into another solid, right? As is indicated here, the relative concentrations of things like aluminum go up, silicon goes down, sodium goes away. So the way we track this process is different than the way we track this process. In this process, we can just look at the water and say, oh, what's the relative proportion of solid and liquid, and what's the concentration of A or whatever in the water, and that will tell us. We could also just look at the volume of the solids and see how they've changed. In this case here, there's a little bit more nuance. This is just another example of another kind of process. This is more of a chemical leaching process where somehow, all the way up to the boundary, the silicon and aluminum don't change, but sodium is being pulled out. Now this process, and we're going to talk about this, both of these in a lot of detail in the semester, this is usually the result of something replacing sodium. The mineral isn't changing, but sodium is being pulled out of that mineral. It's a positive ion. It's usually being replaced by something else. A common thing it could be replaced with is potassium ions coming out of solution. If we had a plot of potassium here, we would see it. That's something called ion exchange. Non-stoichiometric chemical reaction, but very important for water quality conditions. Okay, so now when we think about the TDS in a water, we have to think about two things: the dissolution, congruent, incongruent, and the extent of dissolution. And the extent is governed by solubility. We're going to talk about solubility in a second. Things that are very soluble really dissolve into water that contribute a lot of solute. Things that are sparingly soluble don't contribute a lot of solute. And the extent of dissolution is not only governed by how soluble a material is, but physically, how is that solid presented to the water? Is it a big chunk of rock without any porosity or any ability of water to flow through it? Or is it rock that has some kind of texture, a fracture pattern, or an internal porosity, or it's ground up into small grains? Anything that increases the surface area increases the rate of dissolution, which can enhance the concentration that water can acquire as it interacts with solids. Now, after we get stuff dissolved, we have to ask the question of, are those things going to stay dissolved or not? And this is something determined by each individual material. Some of them have a high solubility in water, some of them have a low solubility in water. Now, this is where, again, that conservative and non-conservative principles apply. Things that are conservative tend to be higher solubility and less sensitive to whether they're going to stay in water as a function of things like pressure and temperature and pH. Things that are non-conservative, especially very non-conservative, may go into the water and come right back out, usually as a different solid. They may chemically precipitate as something else, and that is governed by their solubility behavior in the presence of things in water that can bond with them. Usually something containing oxygen, could be the water molecules itself, could be oxygen, could be hydroxyl ions. We'll see an example of that in a second. Or from other solubility enhancing ligands. Ligand is a Lewis base that donates electrons to materials as complexes in solution, especially aqueous solution. And these kinds of ligands are specially dissolved organic carbon. Not exclusively, we can find other kinds of ligands, but DOC becomes really important here. So how something dissolves and what happens to it once it dissolves affects what the composition of a water is going to be as it migrates through the landscape. So these are just some definitions. Solubility is a quantity we can measure. It's usually measured in moles per liter or grams per liter of a solid into a solution at a specific temperature. You can look these things up in tables, Google them, whatever. Saturation is a related term. This is the maximum amount of solute, a particular solute, we can stick into a solution of a given volume at a given temperature, right? And we all know if you can put more stuff, many cases of solid, into hot water than into cold water. That's where the saturation state becomes important. And if you ever made crystals of anything when you were a kid, you would dissolve stuff in hot water, put a little string in, let it cool, stuff would come back out. That's because as it cools, the saturation state gets lower and lower temperature, and so we start to form crystals. Then we have concentration, right? And so, you know, in most chemistry classes, you learn concentration in units of molality, or maybe molarity, or maybe, those are probably the two most common things. And we use them, but in the environmental sciences, we tend to not use them as much as units by weight. And the reason for that is because of how we do our chemical assays, how we make measurements of concentration. The instruments that we use are usually standardized using standards of a certain concentration. A concentration unit is something like a percent. which is a part per 100, or a per mil, which is a part per 1,000. The most common units for most chemicals are ppm, parts per million, right? So if you have 1 ppm of something, that means that in a million grams, for instance, of water, you've got 1 gram of that solvent. Or whatever unit you want to use. These are the 2 SI units for a ppm, a microgram per gram or a milligram per kilogram. You will see both of those in publications. There are also units like ppb, parts per billion, 3 orders of magnitude lower. ppt, parts per trillion, 1,000,000 times lower than that. ppb would be given in, for instance, nanograms per gram. A ppt would be given in picograms per gram, and it goes on and on. You want to be comfortable, though, in using these kinds of units and making sure that when you look in the table, if you see things given with different units, that you normalize so that everything's being compared on the same unit before you make comparisons. So these are some kinds of solubility reactions. In addition to whether something dissolves congruently or incongruently, we have to think about how's the solid put together. So we have ionic solids like sodium chloride, right? Stick it in water, it dissociates, and we get aqueous ions off of them. We can also have covalently bonded stuff like this sugar molecule here, that when it dissolves, the molecule doesn't break apart. It's still identifiable spectroscopically in the solution, but it's soluble. So we go from the solid form to the aqueous form. And then we have covalently or ionically bonded materials that dissolve, but then they react right away with the solution. So right in this case, we find the 2 constituent chemicals of this thing on the product side. But down here, as soon as we dissolve CO2 into water, it dissociates into bicarbonate ions and hydrogen ions. So when we look in our water, we're not going to find any dissolved CO2. This is a very fleetingly present substance. We're going to find bicarbonate. And depending on the pH, there's a very high pH like seawater, we're going to see this continue to dissociate onto carbonate anions. It all depends on how much of this is present. So if we want to say how much carbon dioxide dissolved in our water, we have to think about what the chemical reaction is, how it depends on pH, and reconstruct that from the chemical products of the reaction. Here's another example of a simple magnesium silicate. This might be the pyroxene mineral enstatite, dissolving in water. And again, it creates some magnesium ions. They come right from here. Some dissolved silica comes right from here, and some hydroxide ions. Those hydroxide anions come from the dissolution of this material and the requirement to have electronic neutrality in the solution. So even though we can track how much of this dissolved with something like the amount of this, we at least need to account for the fact that if our water interacts with a lot of natural silicate material, it's going to get basic. It's going to change the pH, and everything else that's pH dependent is going to be affected. And it turns out, over Earth history, these 2 categories of reactions have helped to keep the carbon dioxide in our atmosphere relatively constant. If you think about the rock cycle and the long reach, the arc of sort of where the continents have been and collisions and mountain building and erosion, over that kind of 50 to 100 million year cycle, we can have sort of more or less of this reaction happening and therefore more or less of this happening, which helps to modulate CO2 in the atmosphere. This is not like an anthropogenic climate change kind of time cycle, but these are some of the ways that chemistry does impact things in the absence of humans. All right, so when we talk about solubility, and we're going to do a little bit of quantification here, we want to say how much of a material dissolved. We can look it up in a table. The solubility is usually derived from some simple relationship between the original solid present and the solutes that are formed. The solubility per se is defined as the number of moles of a solid that will dissolve in a substance such as water when it reaches complete equilibrium. And that's, of course, a function of temperature. So we can kind of quantify this in a simple way. Every chemical reaction of a solid dissolving in water has an equilibrium constant associated with it. When we take a solid that fully dissociates congruently, we oftentimes write the equilibrium constant as the concentration of this times this. Solids don't go into our equilibrium constant. And so we call that, we give it the special abbreviation of a KSP, K solubility product. That's all that is. It's just an equilibrium constant, K, but it's a special category solubility product. So when this stuff dissolves, we can look an equilibrium constant up in the table at 25 degrees C or whatever temperature. We can also sort of say, all right, if a mole of this dissolves, it makes a mole of that and a mole of that. So we don't know how much is going to dissolve. Let's just call it X. So if we say X is the amount of sodium that dissolves, X is also going to be the amount of chlorine that dissolves. So X equals these two things, and we can substitute X into this equation and find out that the K solubility equals X squared. X is actually the solubility, the number of moles of stuff that dissolves. So we can rearrange this equation and find out that in this simple case, the solubility is just the square root of the solubility product. Okay, that's just math. We can get a little bit more complicated. We can go to the mineral fluoride. Fluoride is also calcium fluoride. It's a mineral that is ionically bounded and it dissolves congruently in the water, but with a slightly different stoichiometry. 1 mole of this stuff makes a mole of that and 2 moles of that, right? And so we have an equilibrium constant. It's still a KSP, but it's written slightly differently, right? Calcium times fluoride to its stoichiometric coefficient. That means it's fluoride squared. Okay, we can do the same logic that we did before where we set the solubility to X, which is the number of moles of calcium, because 1 mole of this comes from 1 mole of that. And under those circumstances, we're going to get 2 moles of this, right? Because we're getting twice as much. So if we substitute that stuff in here, right, the fluoride is 2 times the calcium. So the solubility product is X for calcium, 2X for the fluoride, and then squared because of its stoichiometric coefficient, which gives us 4x cubed, which we can rewrite to say the solubility of this is the solubility product divided by 4 to the 3rd root. One of the important things about this is that when a mineral like this dissolves, it produces twice as much fluoride in the solution as it does the calcium, and so we get a much more complicated relationship with solubility. But it's still solvable. So here's another reaction. This is a reaction I showed you a few months ago where enstatite reacts with water to make dissolved silica, sometimes called silicious acid, and hydroxide ions. You can also write this equation and it would be correct in this way, where magnesium silicate dissolves with water to make magnesium ions, again, aqueous dissolved silica. So these forms are a little bit different, and hydroxide ions. You'll see the only 2 differences between these equations, excuse me, are the chemical form of the silica and how much water it takes to balance it, right? So we don't put water in our equilibrium constants when we're in aqueous media. So this literally doesn't matter. And whether or not we write our silica this way or this way, it's still a mole, right? So the equilibrium constants for these 2 things are going to look exactly the same. So we take a mole of enstatite and we dissolve it. The simplest thing we can see is that 1 mole of this is going to make a mole of that. So we do that same process. We're going to write out an equilibrium constant, and we are going to put X in for the number of moles of magnesium. We're also going to see that we have a 1-to-1 stoichiometry between magnesium and dissolved silica in both of these cases, but we get 2 times as many hydroxide ions. So we can write out our solubility expression and find out that X, the solubility, is just the equilibrium constant of dissolution divided by 4 to the 1/4. Again, this is, I'm going to show you why these equations are important, because we're going to plot them up against each other and see how we use these relationships to understand what is controlling things like the pH of water and the magnesium content in a natural environment. So think again about the incongruent reaction that I just showed you before. Whether or not something is reacting congruently or incongruently, we can still define solubility by finding something that is produced into the water by that dissolution reaction and looking at its stoichiometric relationship back to the original solid it came from, right? So if we have something that, for instance, in this case, it looks like sodium is at some value and it goes to 0 when we do this incongruent reaction. Yes, aluminum goes up, yes, silicon goes up, but we can say that for each amount of this substance that dissolves, it completely loses its sodium. That means that a mole of solid is producing a mole of sodium into solution. We can still track the solubility even though the product of dissolution is a new solid, by looking for the thing that is liberated. So this is that same reaction, now for a slightly different mineral. This is potassium feldspar instead of sodium feldspar. This is kaolinite. These are just pictures of what these two things look like. Kaolinite, a very common clay mineral, the sort of end product of very intense chemical weathering. And it consumes hydrogen ions. In the process, it produces potassium ions and dissolved silica in the process, and it would result in a concentration profile just like this, where it would say potassium here instead of sodium, if we look in the solids. And so we can write out the solubility expression, again, just doing that same thing. Yeah, a mole of this stuff, when it dissolves, it makes a mole of that, right? Because there's 2 and 2, and it consumes a mole of that, and it produces twice as many moles of dissolved silica. We can plug in a bunch of stuff there and come up with an equilibrium constant for this, recognizing that this reaction is also dependent on the pH because we have hydrogen ions, which will go in there to the square in an equilibrium constant. So, this is what the equilibrium constant for this reaction looks like. And what I want to kind of point out is that we can plot this up in space if we take the logarithm of both sides of this reaction. So we take the log of the equilibrium constant, it's just some other value, it's called log equilibrium. You'll actually see that in some cases, just like in pH, which is the minus log of the concentration of something, sometimes these are given in P units, which just means the minus log of something. So you might see a minus PK instead of a PK, which is the minus of a log K. But in any event, if you remember your algebra of logarithms, where things that are multiplied become added, we can separate this out into an equation that says the logarithm of the equilibrium constant is 4 times the logarithm of dissolved silica plus 2 times the logarithm of the ratio of potassium to hydrogen, and derive an expression that's a line y equals mx plus b, where we're relating this value to the variation in the ratio of the ion that is produced to hydrogen ions and the another one of the chemicals that are produced. You can rearrange these however you want. You could write one of these equations where pH is on one axis and the other solutes are on another axis, but this tends to be a useful way to figure out how much dissolved silica are we getting in water from dissolution of one mineral. We plot this up on a diagram, we'll do that in a second. And then we take a whole bunch of other minerals, we put them all together, and then we say, oh, okay, under what conditions will this mineral or that mineral dissolve and give us compositional attributes? Okay, so this is what that looks like on a line, on a diagram of log dissolved silica versus log of potassium ions over hydrogen ions. So just a line, and that line separates the fields where at chemical equilibrium will either have potassium feldspar or kaolinite. We can also predict the composition of waters to some extent. Like if we know we've got both those solids present in their chemical equilibrium, then our water must be somewhere along this line. And if we can independently measure the pH, then we can pick off exactly the potassium concentration that we expect from it. Now we can add some other lines onto this diagram. So this is a slightly more complicated diagram. That's that same line. But there's some other things that affect the constituents in the solution, such as the solubility of amorphous silica. So it turns out that if silica gets too high, it comes out of solution, not by the transformation of kaolinite and feldspar, but by precipitating the amorphous silica, right? So we can't get to silica concentrations higher than this value. So we add this line into here, and what it does is take this field, which used to be this thing, and it chops it off. So only this part becomes available. So this is a phase diagram, which shows that what we expect to find, kaolinite, potassium feldspar, or either of these minerals along with the amorphous silica precipitate if we're at too high of a value. So again, this is a pretty simple situation. And we show these lines as dashed lines because they shouldn't exist, because this line is truncated by this line, but sometimes in chemical reactions happen very fast. You can imagine that, for instance, the precipitation of amorphous silica may take more time than the dissolution reaction here. We can sometimes find ourselves over the line. Eventually, we'll move back. That's the difference between chemical kinetics, which is the rate of processes, and chemical equilibrium, which is the end point of the process once all the dust is settled. So this is another diagram extended now down on this axis a lot more. That's that same, this is the same diagram up here, the same line that we were looking at. These are just some natural waters on here. So we've got the dissolved silica line here. We've also got a solubility of quartz line. We've taken this to lower values and this to lower values. And these are just some natural waters on that diagram. And you can see that some of the waters seem to follow some lines. So that maybe that gives us the idea that, for instance, the solubility relationship between potassium mica and kielinite may be affecting in some way the composition of potassium in seawater. Some of these other things sit between lines, which means that the concentrations are not being controlled by them, but at different concentrations or situations, we may find different minerals present and other things whose solubility depends on, for instance, how much silica is in solution or what the pH of the solution may correspondingly vary, especially for the non-conservative ions. So this is another diagram. This is for magnesium. Same story. I'm not going to go through each mineral separately. I'm just going to show you the whole pantheon of magnesium silicate minerals that we find in typical rocks and the fields through which they intersect at 25 degrees C in a diagram now of log magnesium over hydrogen instead of potassium and log of dissolved silica. And this is the field of natural solutions, meaning if we get to higher silica concentration, we bump up against our amorphous silica line. And if we get to high enough concentration of magnesium, something comes out. In this case, it happens to be the mineral magnesite, the magnesium carbonate. But if we happen to intersect a line over here, it's going to be serpentine. If we happen to interact over here, it's sapiolite. And all these other minerals, even though they dissolve and they will react into something else, we shouldn't find them in a natural water at chemical equilibrium because their lines don't intersect that field, if that makes sense. They require more silica than a water can have. So again, if we go into an environment, this might be really important, for instance, a geothermal environment where these fields change their size and shape and these lines move around a little bit as a function of temperature. And we find, for instance, one of these minerals in equilibrium or apparent equilibrium with the water, and then we can usually tell that by looking at the textures of the minerals, then we might be able to do something about what temperature conditions that stuff formed at. Or we might say that some non-equilibrium process has taken place that allows us to have one of these minerals even though we don't predict it. The next slide is not meant to freak you out, but it's just all the equations for each one of these things, just in case you want to derive any of them for yourself. Hopefully it's not too hard to see, but these are the reactions. Each one of those lines has a reaction and it has an equation in the form of y equals mx plus b. I don't expect you to memorize this. You're not going to solve any problems using it. You can find these things for yourself, or you can look up diagrams like this. There are even now programs that you can use that do these calculations for you simultaneously, right? So you can say, oh, what are all the magnesium-bearing mineral reactions and sodium and potassium and everything else, and what's my water going to look like? And it will basically just tell you the answer. But it's important to know where it comes from. It's really very simple chemistry. Okay, so our last topic today, segueing a little bit, is complexes. Does everyone remember that term somewhere? If you take vitamins, you will see complex materials, chelates. For instance, vitamin B12 is a chelate of cobalt. A chelate is a particular kind of complex. A complex is an association of materials in solution that are connected together but not quite as strong as a chemical bond. It's a chemical interaction that's stronger than a van der Waals interaction, like a hydrogen bond, and weaker than a true chemical bond, but it makes identifiable materials in solution with geometric patterns that form because of Lewis acid, Lewis base interactions between materials. Now, I think, if you look at the chemistry review pack, I go through the definition of a Bronsted acid and base, hydrogen ions, hydroxide ions. That's a traditional way of thinking about acids and bases. But a more general way to think about acids and bases is the Lewis acid base definition. A Lewis acid is deficient in electrons. A Lewis base is excessive in electrons. You have to look at the valence electrons, think about Lewis dot structures. It's the same Lewis. And what does a particular material need to have a filled valence shell around all of the constituent atoms? Some things that don't come with enough electrons on them by themselves need to pull something to them. They are electron deficient. Boron is a great example with 3 valence electrons. It wants to pull stuff towards it, so it makes it a Lewis acid. A Lewis base is something that's like, yeah, I got extra electrons. I'm cool, I will donate one, okay? And so another way to think about Lewis acids and Lewis bases as electron acceptors and electron donors. I should have written this as acceptor donor because a Lewis acid is an acceptor of electrons and a Lewis base is a donor of electrons. In a complex where we've got either something that is electron deficient at the center and we park a bunch of electron donors around it, or something that's electron excessive at the center and we park a bunch of electron acceptors around it, we make this geometric arrangements, which we call complex. And again, this has gone into in detail in the review pack. I'm going to go through a little bit more on the next few slides, but we're going to talk about complexes and the special category of complexes called chelates. So another useful term to recognize is that something that is donating electrons, something that's a Lewis base, is also called a ligand. Okay, and ligands are simply chemicals in solution that are willing to partially share some of their electrons with something else that needs it. Okay, so I've defined the Bronsted acids and bases on this slide in case you don't remember those terms. Now I'll give you a very simple example of a complex. This is a hydrate. A hydrate is a special kind of complex where, for instance, we have some dissolved iron ions in the +2 form. Some water molecules park themselves around it. This is something that is electron deficient. It's a Lewis acid. Water, as we talked about last time, is a polar molecule. It's got a positive side and a negative side. It can park its negative side next to that iron and help make that iron ion feel a little bit less electronically vulnerable in solution. Okay, and so it's not a transfer of electrons, it's not a chemical reaction, it's a weak association. And in fact, because of the geometry of the situation, which is the size of the ion, the size of the ligand, and the density of charge, we can park 6 waters around that, which makes a complex, which we call a hexahydrate. It's still got the same charge, right? Iron started with 2+, the complex still has a 2+. We don't park 4 water molecules, we don't park 8 water molecules, we park 6 water molecules. So, which is a very common type of coordination, which we happen to call octahedral. There are other cases with other ions and other ligands where we may make something that's tetrahedral, which is 4 things around it, or other organizations, but those are the 2 most common. So this is an example of a complex, a really simple complex. Now, we mentioned the word ligand. Ligands are Lewis bases. Lewis bases are often shown in solution as being those 2 dots. If you remember back to doing Lewis dot structures, they're just a free pair of electrons, right? So in the case of water, this molecule actually has 2 dots here and 2 dots here. This is sp3 hybridization. There are 2 electrons in this bond, 2 in this bond, and 2 in these lone pairs. But in general, a molecule can't donate 2 sets of electrons. They're just too close together. So that would still only donate 1 set of electrons. So that ligand would be depicted like this. It's monodentate, meaning it's got 1 pair of electrons in its Lewis base chemical component that it can donate to something that is a Lewis acid, in this case shown as M for a metal. We can also have what we call bidentate ligands. ligands that happen to have 2 electrons that can be donated. And we can have tridentate and we can polydentate. We'll see that natural dissolved organic matter is typically polydentate. Now, if we take a polydentate ligand and we donate multiple pairs of electrons to the Lewis acid, we make something called a chelate. That's all the term chelate is. All of these are complexes, right? But they only become chelates when we start to have polydentate ligands interacting with individual Lewis acids. So this just explains what I said about unidentate ligands. And there is a chemical constant, an equilibrium constant, if you will, of formation for different complexes, such that if we stick a single Lewis acid in solution with a mixture of Lewis bases, we can get a multitude of complexes. And the proportion of the complexes we get is largely a function of what is the preference of that particular ion for those 2 particular ligands. So for instance, I've given you an example now of iron 3, different oxidation state of iron, much less soluble form of iron, but it's the common form we find at the surface of the earth where there's oxygen. In the presence of a solution that not only has water, it's got chloride ions and ammonium ions. So ammonium ions have a free pair of electrons. Chloride ions have multiple free pairs of electrons. If you remember anything about your introductory chemistry, you remember that chloride has a very high electronegativity. It really like to share its electrons. And the whole concept of making complexes, Lewis acids, Lewis bases, is the concept of sharing. So chloride is present, and you will find some chloride complexes, some of these iron hexachloro complexes, for instance. But in the presence of ammonia, it's much more likely to find the hexaamine complex because of the chemical properties of chlorine. You can look up what the equilibrium constants of formation are, and you can get these mixed complexes too. And the important thing I want you to note here is what is the charge on the complex, right? So in the case of taking iron and adding water to it, the water didn't come with any charge. The complex stayed the same in charge. If we go back and look at this slide here, right? Iron plus 2, iron hexahydrate plus 2. But in the case of our ligands having a charge, if we take a 3+ iron and we add 6 negatively charged chloride ions, the complex shown with brackets has a -2 charge. If we take 6 ammonias, and which have no charge, then the complex stays with +3. And we have these mixed combinations here that have different charges on the complex. So what do you think would happen if we lower the pH of our solution? A lot. Let's say we lower the pH by a couple of orders of magnitude. How do you think it would change the proportions of these things?
Towards the iron part.
Exactly. Because ammonia converts to ammonium, and when it's in the NH4+ form, it won't make a complex. So this is a pH sensitive kind of situation. And again, this is a really simple one, but in natural solutions, we have lots of different ligands. There's always a competition between things that are or aren't going to donate to individual chemicals. So this is an example of a very simple bidentate ligand, ethylene diamine. Ethylene, because it's got 2 carbons, and again, we'll go through the organic nomenclature later in the semester, but it's just a 2-carbon molecule with an ammonia stuck to each one. When ammonia becomes combined into an organic molecule, we call it an amine. So this is a diamine. It's chemically analogous to NH3, except one of the nitrogen-hydrogen bonds is replaced with a nitrogen-carbon bond. So there's still a lone pair of electrons here and a lone pair of electrons here. And this can both bind to a metal, 2 separate ligands, so it's a bidentate metal. This is an example of a metal EDTA chelate. EDTA, which is something that you see all the time on labels. Again, it's used as food stabilizers because it helps to solubilize metals. EDTA is taking this molecule and replacing each one of these hydrogens with an acetic acid residue. Acetic acid residue looks like this: carbon, carbon, oxygen. When it's acetic acid, it's an OH, but this ionizes at relatively low pH. So this is one acetate anion. This is another acetate anion. Those dashed lines are just meant to imply that this is a 3-dimensional structure, and this is pointing away from you. these are pointing for you. That's in the plane of the back of the screen. Here's another acetate and another acetate. So this molecule, EDTA, has 6 different pairs of electrons it can donate to a single metal. It's got the pair of electrons on each of the nitrogens, and each one of these acetate anions can also donate a pair of electrons. So this is a very, very strong complex. It turns out that the more pairs of electrons a single molecule can donate to a metal, the stronger the complex. And it's largely because of entropy reasons when they form. And so this kind of thing is common in natural organic substances, the ability to make these polydentate complexes. So these kinds of chelates are very common in the presence of organic matters. Some organic or chelate agents or Lewis bases or ligands, polydentate ligands, are so good at solubilizing metal they can leach things from pipes. Textbook has an example of a chemical called NTA, which is nitrotriacetic acid, that can actually suck lead out of pipes because it's so good at solubilizing lead that it will take it from the solid form if it's present in the water. And this happened to be a chemical that was used very frequently as a degreasing agent in auto body shops for cleaning parts. Dump down the drain or whatever, it gets into the water, wastewater situation, and then it can suck up lead. It's not like anyone wanted to do that. They weren't even necessarily aware it was going to do that. Another thing that has a lot of natural chelates is something that we call the humic substances. This is a generic term that's used to talk about biological macromolecules formed by photosynthesizing organisms in the environment. We're going to define it in more detail. It can be separated up into certain categories: humic acid, fulvic acid, and humin, which are different components of this that are soluble at different levels of pH. But the important thing about them for now to realize is they're large biomolecules. They're not an individual chemical. They are a group of chemicals with water solubility characteristics that are similar. And what's common about them is that they are all polydentate and can, like other things, solubilize metals. And they are one of the main things that helps determine, as I said before, the solubility of all these elements from each other. Okay, so the very last thing we want to talk about are the behavior of ions in water. How something decides to dissolve in water as an ion is going to be a function of, well, how does it interact with oxygen? Oxygen in the form of H2O, in the form of OH minus, in the form of H3O plus, and in the form of dissolved oxygen if it's present. Okay, and so we can look at that as a simple chemical reaction. For instance, look at this hydrate complex here, where we've got some metal with a positive charge of N, and we've got some water. And if these two things don't want to interact with each other, right, at all to make a chemical bond, we'll end up with a complex where there's this loose affiliation, something stronger than the van der Waals force. In this case, there's 4 things, so it's tetrahedral arrangement, and things stay that way. But if we have a chemical that wants to make a covalent bond with oxygen, more so than oxygen wants to make a covalent bond with hydrogen, we will transfer electrons from this bond to make a new chemical, a hydroxide, in front with a central ion. Okay, and the propensity to do that is a function of 2 things: the electronegativity of that center ion and its size. Right, there are certain sizes and shapes that work, and certain electronegativity contrasts that work, and others that don't. And so those 2 things, electronegativity and ion size, go together. And in fact, we put them together into a term called ionic potential, which I will show you in a second, which is essentially a measure of how effective of a covalent bond do we want to make between our metal and oxygen. So for instance, this is the process of taking the electrons from this bond and transferring to the metal and making a new chemical, a hydroxide chemical where the charge is lower by 1. And we've also made the water acidic, if you notice. We could do this ad infinitum, right? We could do this 4 times and change the charge on this molecule sufficiently more and make the water much more acidic. Or we can leave it with 1, or we can leave it with none. And it all depends on the properties of that element X. So these are plots of the charge than the radius of the ion. I've given you two different charts because they show slightly different things, but it's important to note that the axes are flipped. So we got radius, charge, and over here we've got charge and radius. The important thing to note is that the field in green, the ones that are intermediate in terms of these two parameters, are the very unsoluble chemical elements in the periodic chart. And they're the ones that are in here in the center. So the ones over here and over here on the two extremes fit into these two categories. These are the things on the right side of the chart. You can see some of these things that make oxyanions that you're familiar with: phosphate, nitrate, carbonate, sulfate, etc. The things that make cations, the stuff that's all the way over on the other side, potassium and sodium and magnesium, etc. These tend to be pretty soluble. These tend to not be very soluble. This is just a table of putting those two things together. If we take the charge over the radius, we get a term called ionic potential. I just color coded them for you. Again, high solubility, moderate solubility to low solubility. And the reason that they're low is because they tend to make neutrally charged chemicals that precipitate out of solution. So now we go to a chemistry that's a little bit more complicated than just stuff in water. Let's put some other ligands in there. Why? They could be chloride, they could be ammonium, they could be organic matter, whatever. We have to look at the Lewis acid-base interactions for every one of those chemicals between our metal and water. And there are cases where we can add stuff to water naturally or by human interactions. Why? That solubilizes this stuff in the center here. There are very few cases where we add stuff to water and these things that were already soluble become insoluble. They're pretty much soluble anyway. But these guys in the middle can become solubilized, especially by adding in organic matter. So this is a table that just shows you the composition of seawater. Periodic chart, the height of the bar, these are log scales, shows you how much stuff is dissolved. The two ends of the periodic chart higher because, in part, this ionic potential thing. There are also other parameters here, such as the relative abundances of the elements in the rocks that are being weathered to make seawater, which is some of what makes the bars decrease as we go down through the various periods. But in any event, this phenomena is one of the key things that governs solubility, and those are our sparingly soluble elements. Now, natural organic matter, and this is an example of a type of humic substance called a fulvic acid, the most water soluble. We'll talk about what this chemistry means later, but the thing I want you to see for now is all these things labeled COOH. Those are acetate anions, just like we have in EDTA. So this particular molecule has 1, 2, 3, 4, 5, 6 of those, right? Each one of those can donate electrons, as well as these hydroxyl groups and these ketone carbonyls. They're a little bit less effective at donating electrons, but they can. This is an example of a natural chelating agent that exists in natural waters from a watershed where there are plants living in the environment, contributing to the soil. These are things that can help solubilize our sparingly soluble elements, these ones here. Okay, so all of a sudden we realize that if we're in an environment with a high biomass, we have more of those chemicals being presented to the water and more ability to solubilize our sparingly soluble things. This is the last slide. This is the extra level of complication that makes our lives difficult in the environmental sciences, which are particle surface interactions. So far, we just talked about what happens in water. Add some stuff, change around some solubilities. Well, it turns out that on the surface of a particle, we have chemical things that interact with water just like they were dissolved, even though they're not. This is an example of a clay mineral with a hydroxide ion. That hydroxide ion can absorb hydrogen from solution and become positive, or it can donate hydrogen, act like a base, and become negative. Certain particles will do this a lot so that their surfaces become positively charged or negatively charged. They attract chemicals to them, which then changes their solubility in solution. So we will go through this process in gory detail in coming lectures. Hopefully what all of this illustrates is that there are a lot of simple chemical principles that can be applied, but when we start to get into the real world where things become complicated, we have to start to think about phase interactions that are much more sophisticated than you would by looking at sort of chemistry in a beaker in a lab. Just the flow field of the water, which determines whether or not particles are suspended with the water or settling out, is going to affect the rate at which these kinds of charged particle surfaces can interact with the solutes in solution. All right, so questions? Is most of this new or some of it still feeling reviewed? Good, okay, perfect. Then that's why you guys have a question. But if you do, send me an email.
Have a textbook.
Yes.